Alright, this is another topic from chapter 6, and this topic is about motional EMF. Okay, so what do we mean by motional EMF? So, the EMF which is induced across the ends of a conductor which is moving in a magnetic field. So, that EMF, right, is known as motional EMF. So, let us discuss about this motional EMF from Faraday's laws. Okay. Okay. So if you remember, Faraday says that the EMF will be induced in a coil or in a conductor as long as there is a change in a magnetic field that is linked with the coil or a conductor. And the magnitude of that EMF, it is given as minus d phi upon dt, right? Where d phi upon dt is known as the rate of change of magnetic flux. Okay. So now let us obtain this motional EMF using this Faraday's laws. So look at this figure. We have, a conductor PQRS here, in which this conductor PQ, it is, it can be moved, right? It can move along this U-shaped conducting rail, all right? And this conductor, okay, it is placed in a uniform magnetic field which is acting perpendicular to the planes of the paper, to the plane of the boat in this case I can say. Alright, now let us say that this conductor PQ, which is movable in this case, let's say it has got a length L. Alright, now if this conductor PQ, it is moving towards left, okay, with a velocity V, then what will happen? So look here, as the conductor is moving this side, then you will find that the magnetic field lines, or we can say the magnetic flux, which is passing through this closed loop PQRS, that magnetic flux will starts decreasing. So due to the decrease in the magnetic flux, then, right, we will get what? An EMF. Okay. So this EMF here, it can be, right, obtained in this way. Let's say at any instant of time, the side QR, let's say it is small x. Okay. Now what is the area of this loop at any time t? At a time t. What is the area of the loop? Let's say the area is A. And this A, right, using this formula, it will be length into breadth, which means L into x. So that is the area of the loop at the instant of time t. So if this is the area of the loop, then we defined a magnetic flux as phi is equals to BA. Or I can say phi is equals to B. Instead of A, I will write LX. Okay. Now, if you differentiate this equation, both sides with respect to time, then you will get d phi upon dt, and right hand side will be d dt of BLX, or d phi upon dt is equals to, okay, because this B and L are constant in this case, so we will take them outside and we will just differentiate only x. Okay, but you know that this dx upon dt, it is the velocity. Okay, it is the velocity. All right. So if you write only velocity, I think this is incomplete, because when you look at the directions of velocity here, this velocity, right, it is approaching in this side. That means the velocity, it is moving in the regions of a smaller magnetic field. So because of that, I will say that this dx upon dt, it is not just v, but it will be minus v. Okay, so that is why if you write minus, then I'll get here. Okay, so please note down this minus sign. It is because why? The directions of the velocity in this case, it is along the decreasing magnetic field. So then if you take this minus here, then I'll get minus d phi upon dt is equals to BLV. Alright, so this is my equation number 1, equation number 2, and I'll name this as equation number 1. Okay. Equation 1 is from Faraday's law, and this equation 2, it is actually when I consider the motions of the conductor through a uniform magnetic field which is acting perpendicular to the plane of the board. So comparing the two equations, alright, we have this is minus d phi upon dt is equals to E, and whereas in this case minus d phi upon dt is equals to BLV. So therefore I can say that this EMF in this case, it is equals to BLV. So this is the equations of the motional EMF which is acting in this case. Alright. So because of the presence of this EMF, then the current should flow through this conducting loop. Alright. So because of this EMF, right, the current, as I said, it will flow through the loop. And now where is the directions of current? The directions of current here can be obtained by using a Fleming left hand rule. It's right hand, not left hand, right hand rule. So according to Fleming right hand rule, it says like this. This is my right hand. If you stretch the four fingers, the central finger and the thumb, and if this central finger points in the directions of magnetic field, okay, and this thumb, okay, my thumb stands for the motions or the directions of motions of the conductor, then my central finger will give the directions of current. So that means the current here, it will pass right in the loop along the direction P, Q, R, S. So that is why I have shown here this current, right, which is the directions of current along P, Q, R, S in this way. So this is the directions of current which is passing through the loop PQRS when this conductor PQ, it is moving in regions of uniform magnetic field. Okay. So similarly, this is the derivations of the motional EMF from Faraday's law. Okay. So now let me obtain the same EMF by using the concept of Lenz's law. Okay, so from Lenz's law. Okay, if you remember, Lenz's law says that the current which is induced in the coil or the current induced in the conductor will flow in such a direction so as to oppose the cause that produces the the current. All right. Okay, so for that, let us again consider this conductor PQ which is movable. So as you know, conductor contain a large number of free electrons. So when the conductor is stationary, these free electrons also are stationary. And if the conductor is moved, right, if the conductor move, then the free electrons also are moving in the directions of motions of the conductor. Alright, so looking at this figure, if this conductor PQ, it is moving with a velocity v in this direction, then it means that all the free electrons which are inside the conductor also will be moving in the directions of the velocity v of the conductor. Okay. Now, if these electrons are moving now, so these electrons, they are actually under the actions of a magnetic field. So if you remember in the in the previous chapter, we have seen that When a charged particle is moving in a uniform magnetic field, then that charge always experience a force. And the force which is experienced by the charge in a magnetic field is given as Fm, and this force is equals to Q V B sine theta, where theta here is the angle between V and B. But in this case, the the magnetic field is directed inward, and the force, the velocity is acting in this way. So the angle between V and B is 90 degree. So when this angle is 90, it means sine nt will be 1. So sine nt will be 1. So 1 times QVB will be just QVB. Okay. So this is the magnetic force which is experienced by the charge in a uniform magnetic field B. Okay. Now, where is the direction of this magnetic force? The directions of the magnetic force, right, can be obtained using what? Fleming left hand rule. Okay. Fleming left hand rule. So this Fleming left hand rule, it tells you about what? It tells you about the force. Whereas Fleming right hand rule, it tells you about the directions of current. So please note down the difference between these two fingers, these two rules, Fleming left hand and Fleming right hand. Okay, so applying this Fleming left hand rule, right, to find out where is the directions of the force which is experienced by these electrons in the conductor. Okay, let me come to Fleming left hand rule. The four fingers give the magnetic field. This central fingers the motions of positive charge, and this thumb will give the directions of the magnetic force. Alright, so looking here, I will do like this. This is my magnetic field. This is the thumb, okay, which is acting in this way. The central finger, and this thumb, it is pointing downward, which means the magnetic force which is experienced in this case will be downward. So this downward force, it is when the charge Q here is positive. So we apply that Fleming left hand rule. But when the charge is negative, like the charge that are moving in the regions of magnetic field is what? Is electrons. So electrons is a negative charge. So therefore that force which is experienced by the electrons, it will be just opposite to this. If the positive charge experience a downward force, then the electrons will experience an upward force. Okay, so that means all electrons will be accumulated at this point, and all positive charges will be accumulated at point Q. Alright? Okay. So now, because we are having two excess charges at the two ends of the conductor, then we will have an electric field which is acting, from Q to P. Alright, because we know electric field is always directed from positive to negative charge. Okay, so again, these free electrons which are moving in a magnetic field, they will experience not just the magnetic force, but they will also experience what? An electric force, because of this electric field which is acting up. And the electric force which is experienced by a charge Q, it is actually equals to Q times E. This is the electric force. And where is the directions of the electric force? The directions of the electric force is along the direction of the motion of the positive charge. Okay, if this is the electric field which is directed from Q to P, then the positive charge, right, would experience an electric force in the upward direction. But here the charges which are under the influence of electric field, it is the electron. So therefore these electrons, right, they will experience an electric force in the downward direction. Okay, so please note down this. Magnetic force, it is F. Electric force, it is down. Okay, now this accumulations of the positive and negative charges at the two ends of the conductor will continue till the two forces, right, becomes equal. All right, so which means at equilibrium position you will have Fm is equals to Fe, or I can say QVB is equals to QE, or this Q with Q cancel, so just VB is equals to E. Alright, so what is B? Magnetic field. What is E? Electric field. Okay, so now after this, look at this figure once again. Because of this electric field, then we have what? Electric potential difference. Okay, because one end is positive, another end is negative, so therefore there is a difference of potential between this point Q and point P. So I will write here the potential difference across the ends of a conductor is, let me write as V. So this V means, okay, don't get confused. Okay, V here, okay, I have denoted the velocity of the motions of the conductor as small v, but for the potential difference I'll write capital V. And this V, which is the potential difference, it is equals to EL. Okay, I hope you still remember this. Or V here is equals to, how much is E? E here is the electric field, so it is equals to VB and then L. Or this potential difference that exists between the 2 points of the, or the two ends of the conductor PQ, it is known as the motional EMF, because the conductor is in motion, so that's why this V is motional EMF. And so we will write as, let's say with this as the new symbol for motional EMF. So this motional EMF will be VBF. Alright, so again we get the same thing like when we talk about motional EMF using a Faraday's law. Okay, this is always the value. Okay, now again, where is the directions of current? The directions of current can be obtained using Fleming right hand rule. Stretch the thumb, the forefinger, the central finger. The thumb, this forefinger points in the directions of magnetic field. Okay, and this thumb stands for the directions of velocity. So this central finger will give the directions of electric current. So again, the electric current in this case is going in this way. Okay, so this is how we we determined about the directions of current flowing through a conductor in a uniform magnetic field. Okay, again, right, we have not come to the end, because I told you I want to express this Marginal EMF in terms of, from Lenz's law. Okay, so let me extend further, because this PQ, right, now it has a current, and the current in this PQ, it is acting downward like this. Okay, so this is the current, and the magnetic field, it is perpendicular to the board. So now this conductor PQ, right, which carries a current and plays in a magnetic field, so again this conductor also will experience what? A magnetic force. Where is the directions of that magnetic force which is experienced by the conductor PQ? So again, using Fleming left hand rule, four fingers the directions of magnetic field, central fingers the directions of the current, and this thumb now is the directions of the magnetic force which is experienced by a current carrying conductor. Okay, So therefore, it means that this conductor PQ will experience a force F in this direction, Okay, and the expressions of this magnetic force F is equals to I L B sine theta, where I is the current, L is the length of this conductor, B is the magnetic field, and theta is the angle between L and B. So we know L is like this, B is like this. So sine theta means sine 90, and sine 90 is equals to 1. This is the magnetic of the magnetic force. Okay, all right. Okay, so after this, I can say that this force F, right, can also be written as, okay, because you know I. What is I? I is current. So from Ohm's law, we know I is equals to V upon R. Okay, where V is the potential difference and R is the resistance. And the potential difference in this case, right, it is actually the motional EMF, that is small e, I'll write with this symbol, upon R, and R is the resistance of this arm PQ. So, and then if you write I is equals to E by R, then you'll get like this. But how much is E? Your motional EMF is V, B, L, okay? So with this L become L square, and then this B with this B become B square, and then upon R. So this is another expression of the magnetic force which is experienced by the conductor carrying current. Okay, all right. Now, looking at the force of this conductor is experiencing a force towards right. Okay, whereas we are moving this conductor PQ towards left. So that is why, in order to move this conductor PQ towards left, we need to spend energy, right? So as to, a work has to be done against this force F, because the force F is acting that side and you are pushing the conductor this side. So when you push the conductor or when you move the conductor this side, it means some work has to be done against the force F. So that work which you actually spent, to push the conductor this side, then that work will be converted into energy, and that energy is the electrical energy. And that is why we have electric current flow in the closed loop of the conductor, right? So this is nothing, this is Lenz's law, right? Because Lenz's law says that a current will flow in such a direction so as to oppose, the motion or the cause that produces it. Okay, so what is the cause that produces this current? It is this motions of the conductor PQ in this side. But in order to do that, we have to do a work against this force F, which is experienced by the conductor PQ. So this is Lenz's law. Alright, so I hope this topic is clear. Okay, both from Faraday's law and Lenz's law. How do we obtain about motional EMF?